Hello guys, welcome back to my channel. In the previous video we discussed about the output characteristic curve and the transfer characteristic curve of this n-type JFET 2N3819, and we saw how to plot these VI curves. Okay, now in this video I would be going to design the self-biased common source amplifier based on the same FET that we have. So in order to start with this, we have to select a quiescent point on this IV curve that we obtained already in the last video. So I have plotted this VI curve with a DC load line. This black color DC load line, as you can see, we have various drain currents and drain to source voltages. The rule of thumb actually is that the drain to source voltage is selected at the midway, at the midway of the maximum VDS that is allowed by the device datasheet. So we swapped this VDS from 0 to 10 volt, so the midway would be 5 volt around, and we have to select the interception of this load line on the VI curve of at a particular gate to source voltage. So the gate to source voltage would be selected in such a way that the drain to source current of the FET would be minimal. This is because the drain current we select minimal because to avoid maximum power dissipation in the transistor itself, that would cause heat dissipation. So we would select the minimum possible value of IDS so that the voltage swing would not cut off at a quiescent point. So in my opinion, the IDS would also be somewhere in between the maximum and the minimum scale, that is 0 milliampere and 12 milliampere. So that would be around this line. Okay, so that would be around 6 milliampere, and this voltage would be 5.3 volt around. We can check this here. We can select this particular graph. This VI curve is actually corresponds to the VGS of 900 millivolt, minus 900 millivolt. So this is 5.30 volt, and the drain current is 5.78 milliampere. So these are the exact values of VDSQ and IDQ. Okay, so 5.3 volt and IDQ 5.78 milliampere. Now if we see the power dissipation at this quiescent point, we get V multiplied by I, simple, and that would be around 5.3 multiplied 5.78, 30.634 milliwatt. Now let's see in the data sheet if this power is within the tolerance of the device itself. So this is the datasheet I have already opened, 2N3819, and the power dissipation here, it says absolute maximum rating is 350 milliwatt. So this power dissipation is well below the maximum power dissipation allowed by this transistor. So we move forward. Now now we have to place the voltage source here. That is a battery source, and this battery would be connected in opposite direction because the voltage is in negative form. .9 volt, that is 900 milliampere, and VDS we can select again the battery. Okay, and that can be 10 volt battery. The halfway of 10 volt is 5 volt, that we selected our VDSQ. Okay, now if this is 10 volt and VDS is 5.3 volt, therefore the voltage drop across the RDS resistor would be 10 minus 5.3. 10 minus 5.3, that is 4.7 volt. 4.7 volt would drop across this RDS resistor, and the current we have selected the quiescent current to be 5.78 milliampere. Therefore, by using Ohm's law, we find RDS is equal to 10 minus 5.3 divided by 5.78 milliampere. So that would give us the value of RDS, 10 minus 5.3 divided by 5.78, that is 0.813 kilo ohm. So we would simply replace this resistor with 0.813 kilo ohms, or in other words 813 ohm. Now the resistor should be connected with between the gate and the source. This is because we have to ensure that the gate current of this JFET is negligible. So we will set the resistor to be equal to 1 meg, and a coupling capacitor can also be placed here. and we will place the voltage source, signal source actually. The signal source, let's take it to be equal to 0.25 volts amplitude and 1 kilohertz signal. Okay, and let it be 1 microfarad capacitor. Okay, now we have to comment this SPICE directive and use another simulation command, that is transient. In this video I will show you the transient simulation. Let it take to be 10 milliseconds stop time, and that's it. Okay, just to tell you about the common source FET amplifier configuration, this is same as the common emitter bipolar junction transistor, in the sense that the output is 180-degree phase shift, out of phase shift with respect to the input. Okay, I have named this node to be equal to V out, and I would name this node to be V in, so we can have easy analysis. Let's save this. Begin, and let's see what V out comes. Okay, so now as you can see that output is having a DC component. As you can see that the output V out is shifted with a DC offset. This is because I have not placed output capacitor, output coupling capacitor. I will place here same capacitor here. Now let's resimulate. Okay, now as you can see that the output and input are 180-degree out of phase with each other, and output is significantly amplified, and we can see with the marker this is actually 1.039 volt positive peak, and negative peak is minus 1.164 volt. That is about 1.16 plus 1.0 2.2 volt peak to peak, 2.2 volt peak to peak. Okay, and our input was 0.5 volt peak to peak. V out comes to be equal to 2.2 volt peak to peak. V in was 0.5 volt peak to peak. Therefore gain would be V out upon V in equals 2.2 divided 0.5. 4.4 volt per volt. Now with this circuit, we can simply remove this DC source, because in practical circuits this is not pragmatic to use a DC battery or coin cell or source. So we have to make a circuit in such a way that the transistor would be self-biased. So in the self-biasing configuration, we remove this battery and we connect this resistor to ground directly, and the gate bias would be provided by the resistor in the source terminal of the FET JFET, and this FET source resistance would be calculated with the formula, and that would be, because we selected the VGSQ equals to minus 0.9 volt. Therefore we have to drop 0.9 volt across this resistor. Okay, and we know that the current flowing through this path, that is the drain path and the source path, is equal. The drain current is equal to the source current in JFETs, because the gate current is nearly equal to 0. So RS, the source resistance, would be equal to ID multiplied by 0.9 volt. Okay, therefore IDQ was 5.78 milliampere multiplied by 0.9 volt. Therefore resistance would be 5.78 multiplied by 0.9 . Hmm. 5.202 milliohms. 5.202 milliohms. So now let's see again what happens with this simulation, as we have removed the DC source from the gate terminal. Okay, so the output is not very interesting. So there can be another there can be a solution for this, and that would be to use a bypass capacitor. The bypass capacitor would render this resistance to act as a short circuit for the signal that is flowing from this resistor. Let's take this capacitor to be equal to 100 microfarad. Okay, for AC signal, this capacitor would act as a short circuit, and this resistor, when parallel with this short circuit, would also become short, and hence there would be no drop of the signal across this resistor. While in the DC, this capacitor would be open, and this resistor would work as a biasing source of this gate. Therefore now let's see what happens. I think there is something wrong with this resistor. Okay, now yes, I think there is some mistake in the formula. The resistance is actually R is equal to V upon I. So yes, so the RS would be 0.9 divided by 5.78 into 1000, 155.7 ohms, 155.7 ohms. So we would replace it with 155.7 ohms. Now let's resimulate. Yes, that is perfect. So guys, as you can see that the voltage has been replicated once again, exactly as we had with the battery, right? As you can see, V out, we move the cursor to the maximum point, that is 1.05 volt peak, and lower peak is minus 1.15, 1.05 plus 1.15, that is 2.2 volt exactly, uh, as we found with the battery biasing. Okay, so this is the common source self bias configuration of FET 2N3819 transistor amplifier. I hope this video was useful for you guys and may have increased your knowledge a bit. Uh, Thank you for watching my video. Kindly subscribe to my channel for more videos and take care. Thank you.